Okay, welcome back. So in this example, we are going to do the same exact problem here, but this time I'm going to do it a slightly different way. What we're going to do is we're going to use this equation right here to figure out what the moment of this force is on the bolt right here when you're turning the wrench in this direction. But what we're going to do is we're going to introduce unit vectors. So what we're going to do is we're going to write out the position vector r in terms of its components and the position vector f in terms of its components. And we'll do this basically the algebraic way. So no real diagrams, no right-hand rule. We are simply going by the rules of unit vector cross products to determine the moment. And so doing it this way will give us the magnitude and the direction all in one. So to start off, I'm going to go ahead and erase all this because this was from the last example. Okay, so how do we do it the mathematical way? Well, this equation right here tells us that in order to get the moment about some point O, and in this case, the O point is right here, the center of the bolt, we need to take the position vector and cross it with the force vector. Well, the force vector is right here, and it's acting this way. Now, the position vector goes from the point of origin all the way to the line of action for this force right here. So the very first thing I want to do is actually draw out a coordinate system, because remember, unit vectors are aligned to specific axes. So the I unit vector goes on the positive x-axis, j goes on the positive y-axis, and so on. So what I'm going to say is I'm going to say that this axis right here is y, and going upwards is positive. And then this axis right here is x, and it's positive to the right. So what this allows us to do is it allows us to express r and f in terms of their unit vectors. So for an example, this r vector right here has a x component and a y component. Why? Because we're dealing with a two-dimensional space right here. We have the x-axis and the y-axis. So let's try to figure out what the components of r are. So r can be expressed as the x component plus the y component. Well, what is the x component? Well, if we're going from this point of origin all the way to this end right here, you can see that the x component has a value of 0.25 meters. So over here, I can say that the x component is 0.25 meters, and because this vector is pointing this way, and this x component is along the x-axis this way, then the unit vector right here, and I'm actually going to erase this because I drew it a little too small, but the unit vector is I, right? It has a component of 0.25 meters, which is this right here, in the I direction. So that's the x component. Well, what about the y direction? Well, if you look at this vector right here, it is pointing exactly in the x direction. In other words, there's no part of this vector that has a y component. So the y component right here is just 0 meters in the j direction. Okay, awesome. So that is r, and obviously r does not have a z component or a k component, but the moment, as you will soon find out, actually does have a k component. But before we get to that, let's go ahead and try to figure out this f vector right here. So f can be expressed, again, just like the position vector, in terms of its x and y components. So if we look at this vector right here, you can see that f is acting straight down, and it doesn't have any orientation in the x direction, this way or this way. So that tells me that the x component is just 0 newtons in the I direction. Now, to that, we want to add the y component of f. And you can see that if f is acting straight down, it is indeed acting along the y-axis. But because the y-axis is going up and this force vector is going down, we know that the y component is negative, right? It's going down. It's going against the positive y direction. So that tells me that the y component is going to be negative. So it's going to be negative 12 newtons in the j direction. Okay, so now that we have our position vector r and our force vector F both expressed in their x and y components, what we can do next is take these two vectors and plug them into this formula right here to figure out what the moment is. Okay, so I just went ahead and did just that. So this equation right here is r, which is this vector right here, crossed with F, which is this vector right here. Now, if you remember, the cross product, we can take advantage of the distributive property, and we can multiply all of these components with one another to figure out what this final moment is. And this moment is going to be expressed in terms of unit vectors because we have unit vectors in this equation. Now, I also want to draw your attention to a diagram that we learned about in the last few videos, I should say. And it was this diagram right here where you had I, you had J, and you had K. And then I drew sort of a circle around them, and I said that this way is positive. So remember, this diagram right here gives us a quick way to figure out the direction of the cross product of two unit vectors. So for an example, if you did I cross J, it would give you K. And because you did the cross product this way, right, I cross J, and this direction right here is the same direction as this big arrow right here, in other words, it's going counterclockwise, then this value is going to be positive. However, if you did it the other way, in other words, J cross I gives you K, you went this way, and you went against this arrow right here. So you would still have a value of K, however, it would be negative. So this diagram is going to be important because we're going to have to distribute and multiply different unit vectors with one another. So let's go ahead and try to do that. So to start off, I'm going to start off with this x component and this x component. So we know that, well, 0.25 meters times 0 newtons is obviously going to be 0. However, when we do I cross I, well, if we look back at this diagram, I cross itself is going to be 0. And that's because anytime you take the cross product of two unit vectors that are the exact same, so I cross I, or J cross J, or K cross K, the value is going to be 0. So this entire term right here just turns out to be 0. Okay, let's do the next distribution. Let's take the same x component and multiply it now with this y value right here. So to this term, to 0, what we're going to do is we're going to multiply 0.25 meters times negative 12 newtons. And in this case, what is the unit vector? So we're doing this term crossed with this term, in other words, I cross J. So if you look back at this diagram, I cross J is going to give us K, but because we did the cross product this way, it's going to be positive. So it's going to simply just be positive K. Now you might be saying, well, we have this negative term right here, and that is true because you're multiplying this scalar quantity times this scalar quantity. But the unit vectors in both of these terms, I and J, is what gives us K. Now, if K was negative, in other words, we didn't do I cross J, and instead we did J cross I, then this K vector would be negative, and that negative and this negative would cancel out, and so this entire term would be positive. But because we're doing I cross J, we're going in this direction, so K is positive, even though this entire term is going to be negative. Okay, awesome. So let's finish this up. Next, we move to this term right here. We're doing the y component crossed with the x component here. And to make this a little quick, 0 cross 0 is obviously just 0, so we can just add 0 to that. And then finally, this term times this term is also going to be 0, so we can just do plus 0. Okay, anyway, let's simplify this out. And this turns out to be, well, this whole thing is 0, this is 0, this is 0. We're only left with this one single term. 0.25 meters times negative 12 newtons is negative 3 Newton meters in the k direction. Now remember, in previous videos, I said that for most cases in at least this course, the counterclockwise direction is going to be positive and the clockwise direction is going to be negative. So because this value is negative, we can see that the moment is acting in this direction and not this direction. And that makes sense. If we look back at this diagram, you can see that the force is going down, so it's causing this wrench to turn this way, and that aligns with this notation, and so we can be sure that this answer right here is correct. Oh, and one more note. Because this is a negative 3 Newton meters acting along the k-axis, remember k is acting along the z-axis, and because this is negative, we know that the moment is actually going into the page.